Can machine learning save the whales? Well, we live on the blue planet, and it's obviously called that because it's mainly water. It's definitely more water than land. And so then it's not that inobvious that ocean health is planet health. I mean, our runoff runs into the ocean, our rains pour the pollution into the ocean, we take our food from the ocean, we play in the ocean. Sometimes we convert salt water into drinking water from the ocean. I mean, we're interconnected. And if we're going to study the effect that ocean health has on biological systems like us, we have to study the mammals within it. And so the turtles, the dolphins, the porpoises, the sea lions, the whales. The whales are the megafauna superstars of the ocean. They're at the top of their food chain, so they concentrate all the toxins within it. And so you can view them as a boundary condition on how bad things have gotten. But also, whales are just awesome, so they're great to study. Some footage I took in Alaska this year, and you can predict when they're going to come up and do that. But there's nothing like seeing the acrobats of the whale species, the humpback whales, do that kind of thing. So they're magnificent creatures, and well, I'm going to tell you the story of their fall and then their comeback and then the mysteries that they're facing now, including these guys, which we find all over the Puget Sound, right? Beloved pods. So I got interested in studying this when I was doing some brain decoding, and I think I've talked about it at this conference before. And I'll provide some parallels between the two topics from a machine learning perspective. But I was out at Princeton working with the Neuroscience Institute, and a team of ours that was filming a piece that's going to be coming out pretty shortly here said, hey, we've got this team, and they've been doing all this great work with whales, and they have a problem. They can't figure out how to apply machine learning to their problems. They've got a lot of data sets, and they have some, they want to mine some information on that. And they told me a little bit about what they were doing. They were taking these drones, and they were flying them really low over these animals. And then just as the animal would come up from a dive, they would collect the spout water, the blowout, in Petri dishes that are strapped to these drones that you can see in the image. That's called a Snot bot. I have a coat. It's like my field jacket, and it says Snot bot on it, and I can't tell you how many times I get stopped with that. I'm sure that people taking pictures of me go, look at that guy, he's a Snot bot. So, but yeah, these have been coined Snot bots, and they're really effective at collecting biological samples from these whales and turning that data into insights. But that's what the work was limited to. So they were DNA sequencing these at OHSU and working with people at the University of Alaska. They were collecting the toxins. They could look for plastics in the water that was in the spout water. They could look for pregnancy hormones and stress hormones and all that. But like I said, their question was, how can we use machine learning to go beyond the wet lab and look at other aspects of what we're seeing out in this environment and try to connect some of the dots that I'll talk to you that they haven't been able to connect between whale health, ocean health, and our own, and with the beautiful side effect of saving these creatures. Now, there was a reason at one time that they were not being saved. We were using them for food. I mean, rightfully so. Whaling is a really old practice. It's gone on for hundreds of years, and there are even tribes and communities that continue this today. And so they are a great source of energy, and including the oil. But we got carried away with this, and as we moved into the last mid-century, we got way too efficient at doing it. We turned out these factory ships, and we hauled out just about every bit of tonnage of whale there was to be, to the point of almost complete collapse. And you can see it in the graphs here. I've got 4 charts that show 6 charts that show 6 species of whale. And you can see that as the century started, this is the haul out of tonnage. So it really is sort of a proxy for how many there are out there. Let's just say that the system got more efficient, the tonnage or the take went up, and then around 1940 it went to near zero. You can probably imagine why for a few years. And then it resumed in full force, and by the 1960s, on just about every one of these graphs, you see that it's suddenly going down. And that was the advent, right before that period was the advent of these factory ships and really efficient harpooning, explosive harpooning mechanisms and tracking and all that. And luckily, through persistent and heavy-handed regulatory action, rightfully so, it stopped for the most part. And so the question is, like, where are we at today? Are these creatures okay? Can we even study them? Are there enough of them to study to understand how bad things have gotten, how well things are doing? Well, more recent data collected right here out of the Strait of Juan de Fuca, that separates Canada from the thumb of Washington. You can see that now we just about knocked them out. Humpback population was one of the greatest populations, and they almost didn't register for many years there. And then recently they've had a comeback for really unbeknownst reasons. They were able to bootstrap and come back in force. This has not been true, though, of all of the species, and the humpbacks are now suffering some very mysterious things. So what's been observed in the last several years is mass strandings that we can't really account for. So like in New Zealand, they've been seeing like 600, this is an example of 600 of the animals coming out of the water voluntarily, leaving their own natural environment, preferring the beach where they're not going to survive because something had threatened them or thrown them off. And that's been happening in waves, and it's gotten to a point of crisis in New Zealand that they're taking like very drastic measures at the government level and the community level to try to take care of this in science. Also, I'll talk a bit more about our trips to Alaska, but we went up there where it's the humpback feeding grounds for the summer, and then they migrate back to Hawaii every winter. And we couldn't even count on one hand how many calves or youngsters we saw this year that were born, and no one knows why. I mean, in fact, there was a call out by NOAA, the government organization that monitors these things, to see if anybody had photographs of these calves, and we only had a couple to offer. Also, I don't know if you've been following it, but on the East Coast, they've been having a crisis with the right whales. Right whales were super popular with whaling. They were called the white whale because they were right whale to kill. They would float when you harpoon them, and they died, and they had a ton of oil. So they got decimated, and they have never come back. There's only 450 in the world or so. And just this year alone, we lost 16 of them to some human-animal interaction and other causes that we're not clear on. And then finally, I mean, you might have noticed if you live in this area that they've been showing up in the bay, and that's not a good thing. I mean, they're right there in the shipping lanes, and they're encountering all kinds of gear and traffic that they shouldn't. And they're there for what reason? Or why have they shifted there? They've also disappeared from other locations. So there's some strange stuff amiss. And that's kind of the state of the affairs. And I just gave a sampling of like the top 4 that came to mind, but there are many mysteries that are happening right now with whales. And of course, the scientists involved, the marine biologists and the great oceanographers, have not been sitting on their laurels. They've been out there collecting data and trying to put together these insights. Just had their, every 2 years they have their major meeting, and it was in Halifax, and I attended, and there's clearly a couple thousand people that care a lot about figuring out these mysteries. Through biopsies and tagging, which are close in on the animals. I show some pictures here of like you really have to put a lot of work into getting a biopsy or getting a tag to track health or track the animals in terms of geospatial. Or people have noticed recently that someone just turned on Google Earth and said, hey, I wonder if I could locate whales, and lo and behold, the scientists found that the whales were always there in Google Earth, and they could track populations and count them. And through underwater acoustics, I just visited Scripps in La Jolla this last week, and they are sitting on petabytes of acoustic data. But the state of the art is not to identify individuals from it, it's just to count and classify the species. So they're a long ways away from connecting the dots from these high-level imagery and acoustics down to the biopsy and tagging level. And there's a big gap in between where most of the mystery lies about what's happening between where they leave Alaska and they show up in Hawaii, or why did they end up in this bay? No one really knows where they came from. So that's the problem. And so what I think is missing is that, like I said, like you can't tag and sample them all. It's way too expensive, and it's very invasive too. And sometimes you put their lives at risk by doing it. And secondly, we've got that problem. We just can't scale that up. We just can't do it. And I also don't think, I mean, we can't wait on satellite technology to help us out or figure out, maybe the acoustic problem is interesting and we're going to take that on, but it's going to take a couple years, several years to figure that one out. So we need a method right now that can help us identify these individuals in a lot more lightweight, light touch way that scales up, and a way of summarizing everything that we're collecting in the samples and how it's really affecting them now in the present, like how are they looking right in front of us. So you can see that I'm alluding to visual data in both cases, and so there hasn't been enough done with that quantitatively. People are doing things with the data old school, okay? So what happens right now is they take land-based photographs with a handheld DSLR, or they go out on inflatables and they do the same, and they take these snapshots almost as an afterthought, and then they pour over these images trying to match. You'd be surprised how hard it is to match like a sea lion to a sea lion or a whale to another instance of that same whale, unless you get lucky enough to get just the right part of the animal. So it's much harder than like facial recognition, and that's what's interesting about it. So they'll pour over these images for weeks, months, and years. In fact, some of them have been trying to catch up with their catalog for 3 years. And they just can't do it. So even if we collect the data, they can't keep up with the processing of it. So technology to the help here. So luckily we did find this partner who was doing all this Snotbot work. This is Ian Kerr, the CEO of Ocean Alliance, sitting there with his Snotbot on top of a small boat up in Alaska with us, and you can see that you can get right over the animals and look down on these great creatures with drones, which really changes the angle and changes the amount of information you can feed to algorithms. And you can do that with lightweight crews, and you can get around and you can do it from any port you're in, and you don't need a specialized crew that's trained in biopsies and has a veterinarian and all this stuff on board. So definitely they showed the potential for the use of, why don't we use the Snotbot as a camera drone? Why don't we collect video and do something else with its sensors? And there's going to be many other sensors coming, right? And look at what you can do. You can get over these creatures. I took these shots of this mother and her calf, and you can clearly see the body. You can see as they dive, also the tail pattern is very distinct. And so we could fly these drones over them, not interfere with their natural behavior, and reach places in airspaces we couldn't before. And these things are the size of a bird. They're out there under birds all the time, and studies have shown that you can't even hear these things underwater. So it's just a great tool for amassing data and feeding it to algorithms. So enter drones and machine learning. We jumped in, drones and whales, cool. How could you say no to that? But also, I strongly believe that innovation comes from the collisions in fields, and there's not a bigger collision than computer science and marine biology and oceanography. It's pretty cool to see that. There's, they need a lot of help. This new data will be new challenges, and new challenges lead to new innovations in neural networks and everything else. So I'm really looking forward to that. And I'll tell you a little bit about it now. So we decided to do two things. We're going to try to identify these whales and then get some sense of how quickly assessing their health from visual data. What was missing for whale identification was it can be done quite well with tails. You can see this pair here, and the trailing edge has an edge pattern to it. And then you can see a little bit of the patchwork. It's the grayscaling that's happening on the surface. It's not so great in this shot, but those two are very distinct markings. And things change over time. A shark takes a bite out of it, or there are a few barnacles here or there. You don't get quite the right shot. But all that was missing here was an algorithm. This one looked like pretty straightforward. Also, then, how do we get their condition? Well, morphometry. So morphometry is the study of an object's shape or an animal's shape to infer meaning from that. And in this case, there have been some really good papers in marine biology about what a healthy whale looks like. They carry their energy stores, they're fasting machines, and they need those to procreate and survive. So you can see in this example, there's some interesting patterns too. This is a healthy mother and calf and an unhealthy mother and calf, and their thinness or robustness, they correlate strongly. The mother is thin, the calf is thin. So it's disturbing, but also interesting. And so if we could quantify what this shape means for these individuals against the population, we would have a lot more information saying, yeah, like standing there with the experts saying, yeah, that one looks pretty healthy, this one not so much. And then looking at that pattern over thousands of animals over regions and trying to put that into a sensible picture, I mean, that's hard to do if you don't have, a really good quantitative method to do it. So that was the other challenge. All right, they sound pretty easy, but you shouldn't ever say that about a problem until you actually go out there and see what's involved in it, right? So we did that. We decided to put the rubber to the road or the boat to the water and hang out in the southeast Gulf of Alaska where all of these humpbacks come every year. I mean, that's where you're going to see most of them up there. And that actually, in red and on Google Earth, is the trajectory we took our boat over a couple of weeks to do this study. We did 2 of these studies, but this is one example. What we found out right away is that like the real world is messy. This is like a whale circus going on here. So we come flying over toward them. They're spouting whenever they want. There are birds flying all over the place. The guy operating the drone's not doing exactly what we want him to. But once in a while you get lucky and you see a shot like that, and you can see the Snot bot collecting see it go right through there? Just collected the spout water. But I'm more interested in the drone that's above that's trying to get the visual analytics on the whole situation, right? So, and this was a good day. You could see these animals quite well. This is not what we faced most times, and I'll show you that. That was one of the big problems. So the key challenges were really threefold. I mean, first of all, no one frame told the whole story on the animal, right? Okay, tell me which of the frames there you would have used to determine its shape. That's an actual shot we took in Alaska, and that was typical. That was more typical of what we got. You see how similar they are to their background. You see how they're never all in view. Sure, you can wait for some crazy LiDAR or NASA-approved technology to look through the water, but marine biologists can't afford that stuff anyway. So we're stuck with like the cameras we have. Okay, so we learned in brain decoding that you tell the story over, like if you're looking at activations of neurons over time as someone does a task while they're sitting in a functional MRI scanner, you piece together the semantic state of their mind over time. You don't do it with one snapshot. And it's similar with this. We're not going to be able to get the visual assessment in one shot. So it's a series analysis. Also, like the signal-noise ratio, you saw that in the last one, but look at this. I mean, discriminating the whale from the background here is challenging, even with good polarization on the filters and so on. There's the reflection distortion of the water, its turbidity. The animal gets its color gets selectively filtered by the water, and there's all this wake it's creating. It's just that way. That's what you're dealing with. You can't just wait for the perfect shot. In fact, you can see it in these shots. I mean, this is an example. I'm going to show you a deep learning network we trained with this, but this is part of the data set, the actual data set that we fed it, and you can look at the variation there and how that relates to what I just told you. But this also points out data starvation. There aren't enough animals to train what you'd consider a state-of-the-art deep learning model without doing some of the recent modern clever tricks with it, and some that we're not aware of yet, clearly. In this case, we thought we had a lot of data, but you end up with maybe a handful of videos, and you've spent tens of thousands of dollars with a crew over many days collecting that. And so you really can't wait for like an ImageNet scale data set to go train the right deep learning network to the accuracy you need. And that was probably the key problem. And I want to talk about how we addressed that in both the photo ID case and the morphometry. So in photo ID, it really started with a shot like that. When they dive, the fluke comes up, you go, the paraflukes, and you go and look for that pattern that I talked about in the trailing edge. And it's, that one is pretty obvious. Like, how are you going to avoid training a deep learning network on this with we didn't have even 10,000 images. So how are you going to train one with 1,000 images? Well, we wanted ImageNet-like performance, or one of these modern models that have been used in the MS COCO, Pascal VOC, or one of those contests. So we've got to do a lot of transfer learning, right? Or avoid learning things that we don't need to throw at the deep learning network and we can do otherwise. So we did rely on the experts here. I mean, lesson one was, like, let's try to pay attention to the features an expert does and use a neural network very selectively, okay? So we selected the tips of this fluke, the notch point, which is in the middle. We found the edge. We can do that quickly automatically. That's quite easy. And then we can do a quick transform, whether it's diffeomorphic or affine or something else, to flatten this thing out on the table for us and capture vectors that represent that edge pattern geometrically, which is what you see on the right side here, or the grayscaling of the fluke pattern across the fluke along a number of directions, for example, and then use that to inform a nearest neighbor search and then look at the ranked results and match, right? And I'll show you how well that worked, but in this case, we decided to selectively use a neural network just to learn how important these features we were selecting were to the problems. This is more classic use of a neural network, not deep learning. But it allowed us to do it with very little data and get sensible accuracy. An early result we got was this, you can see this cumulative distribution, but in a fairly large, well, like the entire humpback whale database for Southeast Alaska, which has thousands of animals, we were able to get top rankings almost every time, so we could have someone quickly triage what we wanted. It would be in the top few almost always, and it would be in the top 10 practically always. So we were very happy because you wouldn't believe how much time that saved them. I mean, they had been doing this for years, matching this with that, doing all these all-way matches, and it was ridiculous. So that saved a lot with a little bit of work, and we actually rolled it out so that it was practical to do on these boats, which meant we could take a standard Intel Core laptop, MacBook Pro or whatever you're using, and wirelessly connect it to the drone. And as it was collecting imagery, we could actually tell you what the match was before that drone landed. And that was, for them, that was a total breakthrough. They had never done anything like that. And this is an actual example we found of a whale that hadn't been seen for 21 years. And what was interesting is we got a hydrophone recording of it, and someone we knew said, "I think I know who that is." And I said, "I bet you we have a fluke match on it then." And we did. It was trumpeter because it's got this really interesting register pitch. Where's David from the previous discussion of music? But trumpeter was an amazing creature to hear. So there you go. Morphometry, we couldn't get around using a deep learning network for this one, so we embraced it. And so the science would say that you measure the amount of energy store they're carrying between like their eyes and about 80% of their length. And then people had been just drawing areas there and predicting, from that their body composite index. It's kind of like our BMI. And really, it amounts to a foreground background segmentation challenge. So that lends itself well. Or deep learning networks lend themselves well to that. So we built on that marine biology, and so we take any of those videos I showed you, we could process quite nicely and try to give that thing X-ray vision, right? And have it paint even parts of the animal that weren't seen. So I'm sure you know by now, as we saw from generative networks earlier, right, that sometimes you think there are lines there that really aren't even there. I mean, they are not there. There's no information if you do an information test on the pixels, right? But your brain is very good at inferring that. And we actually do want it to try to predict where the edge of the whale is, even if we can't quite see it. And it was, we got a network that could do that quite well. And then scale it properly and size it to where the energy store is. And we want to do more research to get more accurate, but this is a good result. The way we did that is we relied on some really great work that came out this year from colleagues and others, this one-shot visual object segmentation. So we fully leveraged an ImageNet trained backbone, and then we used the very precious few videos of whales we had to adapt a parent network. So this is just a name for retraining a selective number of the layers and jiggering the weights so that it was better at doing segmentation problems on whales. And then it's a one-shot network in the sense that when it gets good at segmenting a bunch of things in their example, but we were only interested in whales. At the end, they would show it like a person or something they wanted to ultimately segment in one shot, the first frame of the video, and it would segment the rest of the video automatically. So that's what this OSFOS network's about. So what we said, well, okay, how much better can we do if we just train it on whales specifically? And what if we we can't afford to use the first frame of every video. What's the point of us having a marine biologist hand segment every video they take? How much transfer learning can we do from one type of video in a similar environment, or like you're doing an expedition and it's raining for 5 days, can you use the video you took on the first day to do all the rest? And we wanted to study how accurate it would be at that. So I'd call that one-shot transfer learning. I mean, one-shot transfer learning. So here are the results. I mean, The data set is just this video segmentation set that's out there that was used to adapt ImageNet first. And on the whale problem, like if we use it on whales, you can see the right-hand side, I mean your left-hand side, that it's not doing very well. If we train it on whales specifically, which is the WH, it does pretty good. You know, I mean, we could do much better. I'm giving you a quick and dirty example we did. And then if you do this one-shot transfer learning, the question was how much of a penalty would it be not to retrain it every single time we do a video clip. And it didn't degrade it that bad. It was still much better than the Davis results that they had measured. So we were really excited about that. And I think there's a long way to, we have a bunch of ideas from here, but it meant that this was actually very effective. We fed this thing a couple hundred whale images. That was it. That was the only adaptation we did. And then we gave it one or two segmentations and then used it for days. And, but it does, you know, the graph on the right shows the effect that having segmentation error has on the calculation we're trying to do, and it amplifies. So we have to get much more accurate at segmentation because the error gets compounded, and you know, we're going to lose accuracy really fast in the final calculation. So we also deliver that as an application. It looks a lot like QuickTime. It's not a ripoff of QuickTime, though. And so it's intuitive in that sense, right? But it allows you to process streaming video as it comes in and select the window you want really quickly and send that right over for identification or what we're calling volumetrics or morphometry. So the way the morphometry looked like, here's an example, just one early example we did of it, doing the computation at about the same rate it actually does it in the network and giving a score, which is an average over the series. And this is a pretty healthy whale. So that's about where we're at. We haven't saved the whales, but we have excited that community with what computer scientists and data scientists can do for them. And so that's one call to action for you. I mean, you should talk to me. I have a lot more marine biologists and oceanographers standing by than I have people like you. And I promised them that I would come to Silicon Valley and drag a few of you back, if I had to, in fishing nets, and that I'd get you let loose of some of your time and pay attention to some of these things that are happening around us that are beyond our phones and things like that, although we're trying to send you feeds on this as we're out there doing these expeditions too. But kidding aside, I mean, it's a big time for the ocean. It's kind of at a pivoting point. There I am standing at the UN for World Ocean Day this year where this all kicked off. And it was heartbreaking to hear most of the stories about how things are going out there. And, you know, so we did the expedition, learned from that. We were actually on National Geographic Earth Live this summer. Doing this, the first expedition, and then, but I think the thing I'm most proud of is delivering the science up in Halifax at this biannual conference. And I just want to get more of you recruited to help out with that, because I can only scale my team so much to do that. And you've really got to have a passion for it. But if you find that, you know, I don't know, what's the quote? Tell me what hurts your heart, and I'll tell you what your passion is, or what your life's purpose is. I mean, I truly believe that. So if it resonates with you, let me know. Thank you. And thanks to our team, Javier Turek, Bryn Keller, and Ian Kerr and his team.